Okay, so it's 4:02, so let's get started. So welcome everyone to this week's special seminar, Wednesday seminar. Nils Scheithauer will tell us about deep holes in VOAs, somewhat of a continuation of a talk 1 year ago that everyone are expected to remember, right?
No. First, I thank the organizers for putting up this program and for inviting me. So I will speak about deep holes in vertex of the radar algebras. And I will not assume any knowledge of my previous talk. Okay, so I will start from the beginning. So first of all, I want to say this is joint work with Sven Möller. And yeah, let me start with an introduction which also serves as motivation. Yeah, we start in the 90s. In 1973, Niemeier has shown that there are 24 positive definite even unimodular lattices. So, isomorphism, there are exactly 24 positive definite even unimodular lattices of rank 24. Okay, so this is our starting point. It's not difficult to see that there are actually finitely many lattices with this property. This is a consequence of Minkowski's lattice point theorem. But what is more difficult is to show that there are exactly 24. And there are several proofs available. So the first one by Niemeier. Niemeier proved this using Euler's neighborhood method. Okay, how does this work? So the basic idea is that the neighborhood graph is connected. So what you do is you fix a prime, you take any lattice in this genus, so that means with these properties, and then you determine all its p neighbors, and then the p neighbors of the p neighbors. And in this way, you will get all the lattices in this genus. Okay, this is how Niemeier proved this. Then there's a proof by Borcherds, which uses harmonic zeta series. And then there's another proof, which is the motivation for what will follow, which is due to Borcherds, Conway, and Sloane. And yeah, this is a purely geometric proof. And I will explain this in a minute. There are at least two more proofs. The simplest one is maybe one which uses the Minkowski-Siegel mass formula. So when you have this formula, then this is very easy to prove. On the other hand, the mass formula is not a trivial thing. And then there's an even more sophisticated proof which uses the classification of certain automorphic representations of O24. But for us, this proof here is...
who is that due to, the automorphic representation?
That's described in the book by Scheithauer and Lan. It uses the Arthur trace formula and so on. So it's not not a simple proof, but it gives the same result. Okay, so for us, we will generalize this approach to vertex operator algebras. So that's the reason I could not write black holes here. That would not be possible. I could write quantum deep holes maybe. So, okay, so let me describe this proof in more detail. It has 2 steps. So Borcherds showed that there's a bijection between the deep holes in the Leech lattice and the Niemeier lattices without roots. So the lattices with this property here, positive, definite, even, unimodular, and rank 24, they are called Niemeier lattices. And Borcherds showed that there is a quantum correspondence between the classes of deep holes. I will explain what it is in a minute. In the Leech lattice, and and 23 Niemeier lattices, or the drop 23 here, and the Niemeier lattices with roots. So whenever you have a Niemeier lattice which has some 2 vectors, then there's a deep hole in the Leech lattice corresponding to it. So what is a deep hole? This is just a point in the ambient space which has maximal distance to all points in the Leech lattice. So this is an abstract correspondence, or there's a map which does, and this map or the proof of this result doesn't use anything of the classification. Okay, so that means you can classify these lattices here if you classify the deep holes. Okay, and this is something which was done by Conway, and Sloane. Yeah, of course, we know now what the result will be, but so if you didn't know the theorem, then you would get the theorem from these 2 results. So they showed there are exactly 23 classes of deep holes in the Leech lattice. And you can easily characterize a class by looking at its hole diagram. That's a Duncan diagram. So there are exactly 23 classes of deep holes in the Leech lattice. Each class of such a hole. Maybe I can add something here. Okay. So what I should add, how do you recognize a lattice here? Such a lattice is uniquely determined by its root system. That means if you know, so it's uniquely determined by the geometric properties of the vectors of length 2. So the classification of such, the class of such a hole.
Nils, we have a question
Yes.
on Zoom.
Hello, can you hear me?
Yes.
Okay, so I have a question, which is in order to go up from the 23 to 24. I mean, there's the Leech lattice, but is it clear that this is the unique even self-dual lattice without any roots?
So Borcherds showed in the same paper that the Leech that there's a unique lattice without any roots. So this is in the same lattice.
Oh,
So
okay.
from this you get the classification. From these two results you get the classification, or you do not quite get this here. You need exactly what you did ask, and this is proved in the same paper. So you can show abstractly that there's a unique lattice with these properties which has no root.
Excellent, thank you.
Okay, the class of such a whole is uniquely determined by its whole diagram. Okay. So yeah, if you put these two theorems together, then you almost get this. What you still need is that there's a unique lattice which has no roots, but this can also be shown. And what we want to do is we want to generalize these two results to vertex operator algebras. So we have first to say what is the dipole in the context of vertex operator algebras. And then we have to look whether we can classify them. Okay, and the answer to both problems is positive. So there's a nice generalization of all these two vertex operator. Okay, so maybe often people say vertex algebras are difficult to define or to explain what it is. I'm not of that opinion, but maybe you can decide afterwards or in a few minutes. So we don't need every detail. Okay, so that is the second part. Vertex operator algebras. So I tried to explain in 10 minutes what the vertex operator algebra is. And the basic idea is very simple. So this is just a graded vector space together with a state field correspondent which satisfies some conditions. That's essentially all. The vertex operator algebra is a vector space which is graded by the non-negative integers. Together, the important thing is the state field correspondence. What is this? This is just a map from the space of states, so the elements here, that's what physicists call states. And then you get the series and like this, so you have your state and you associate a field to it, that's the corresponding vertex operator algebra. And this is just the collection of endomorphisms. Yeah, so in principle, you can associate to each element a family of endomorphisms. Okay, and of course, it has to satisfy, this correspondence has to satisfy a number of conditions which are motivated from physics. So there's one which is particularly important, which is that these operators almost commute, not quite, but almost. Particular the fields. So these are these things here. They are local. That means they do not commute. But almost we have to multiply them with a sufficiently high power of this difference here, and then this imposes many conditions on these operators here. So this is true for n sufficiently large, and the bound depends on A and B. And what is also important, B carries an action of the variable. So just to remind you what this is, so that's the algebra. So you take the vector field from the circle, take a central extension. And you have a central element C here. And yeah, this element C here, it acts as a scalar on V, and the number, the corresponding number is the so-called central charge. Okay, so this is a vertex operator algebra. So it's vector space together with the state field correspondence satisfying some conditions. And yeah, in physical terms, well, this is the axiomatic formulation, what a physicist would call a two-dimensional quantum field theory. And there may be two remarks, or maybe three remarks. So usually, so we will assume that V0 is one-dimensional, so we have a unique vacuum. And when we look at the zero modes, they produce a Lie algebra structure on V1. So W1 is a Lie algebra. This will become important because this Lie algebra will tell us a lot about V. Okay. And there are plenty of vertex operator algebras, and the simplest ones are perhaps those which are constructed from lattices.
And Nils, can I just, so if we remove the word operator and just talk about vertex algebras.
Yes.
Which can you remind us which of these conditions we?
Yeah, you lose this property, for example.
Yeah. Okay.
This is one of the properties which you lose. Yeah, for example, that one. And sometimes you even don't demand that you have an action of the so the conditions are depends a bit on yours. Okay. Yeah, so this is one important property. So V1 is the Lie algebra. And the other one is, so yeah, there are plenty of vertex operator algebras, and the simplest ones probably come from lattices. So each operative bracket even lattice L, you can associate vertex operator algebra VL. Okay, so I think it doesn't really, I could write down what it is, but it does not, it's not necessary for us. Okay, so this is essentially all I want to say about vertex operator algebras. So you have a rough idea now what it is, yes?
So in this, I mean, I guess you didn't want to say, but in this case, it's VL, what's the V1, what's the VL?
I will come back to this a bit later. Okay, so the point is yeah, maybe I say it in a few minutes, okay? So it's difficult to say in general what it is, but okay, no, for a lattice, it's not difficult, actually. So if this is a root lattice here, then the V1 is just, so when it is a root lattice, it's of type ADE, and V1 is just the sum of these Lie algebras. Yeah, so yeah, if it's a root lattice, then it's the sum of lattices of type ADE, and then yeah, then the V1 is exactly the direct sum of these Lie algebras. Okay, yeah, this gives you, for example, a very simple construction of the Lie algebra E8. Yeah, you just take the E8 lattice, you take the vertex algebra, the V1 space. Okay. Okay, so this is all I wanted to say about vertex operator algebra. Now we come to poles. Well, how can we define them in this context? And yeah, I will make some assumptions. So I take for V a vertex operator algebra, and I want it to be holomorphic. I will explain what this means. Of central charge 24. Okay, so central charge, I already explained this. So the central element of the Virasoro acts as a scalar, and this is 24. This replaces the rank 24 Niemeier theorem, and the unimodular condition is replaced by this condition here. So this means V is simple. It has to satisfy some regularity conditions. And the most important condition is it has only one irreducible module. So this is the analog of the unimodular lattice in VOA theory. Okay, so we take such a vertex operator algebra, and now we take some automorphism of order n, finite order, and it also has to satisfy some regularity conditions. It must be of type 0 and so on, but I don't want to go too much into detail. I want to present the general picture. So you take some automorphism of order n, then of course you can look at the fixed points, e.g. So this is again a vertex operator algebra. Okay, but this is no longer holomorphic. Yeah, it is still simple and satisfies these regularity conditions, but it has more than one irreducible module. It has actually n squared modules. And you can actually construct these modules, or yeah, in some sense, they can be realized as submodules of the so-called twisted modules. Of the twisted modules VGI. So to each power of G, you can associate an irreducible twisted module, yeah, which is unique, but we don't know much. The problem is we don't know much about these twisted modules except that they exist. And maybe in the lattice case, we can describe them explicitly, but in general, we do not know much about them. But yeah, from the abstract properties, we can show that we can construct these modules as submodules of these here. Okay, so now what is the idea of orbifold theory? So this this BOA is not holomorphic, but we can extend it to a holomorphic BOA, and this is the orbifold corresponding to T. So we take all these twisted modules. If if I is equal to n, then this is the identity, and you will get back our original BOA. So this is almost correct, not quite. So what do I have to do? The group generated by G acts on these twisted modules, and we can look at the fixed points of G. So we do that, and then we add all these things. Then we get actually a new vertex operator algebra, and this is a non-trivial result. And this vertex operator algebra now has only one module, which means that it's holomorphic. Okay, so this is the orbifold construction. And we will need this construction here to define dipoles. So dipoles in the vertex operator algebra context are certain automorphisms. So I will explain this in a few minutes. So what is the problem with this construction here? It's a very beautiful construction. What makes it, one problem is that we don't have much knowledge about these twisted modules, which makes it difficult to understand these BOAs in general. For example, as I already said, the V1 subspace is an important, contains a lot of information. It's just to say what is the dimension of V1 is very difficult. So we don't know much about the V1 subspace. And one of the first results, or the first result which I want to present to you, is the dimension formula for the V1 subspace here. Okay.
Can you construct these submodules through intertwiners or some kind?
Yes, or what prism?
Well, I'm not sure.
You can construct these twisted modules for lattice vertex algebras. They are constructed, or the other ones not. We have some. There are some. Essentially, we only know that they exist.
But I guess so. Scott Carnahan did this for generalized moonshine, right? Intertwiners for the monster orbitals of the monster. Maybe that's.
But we know that they exist, but we have no explicit description of them, except in the lattice case, and I think something is known in the affine case. Okay, so I remove this.
Can I ask a more basic question?
Yes, sure.
So what is a module for a VOA? Like what is the data of a module for V?
You take all the axioms of the BOA essentially, which still makes sense. So you want to like for Lie algebra, so you want to preserve the axioms which can make sense.
Right. So how do you compose or the endomorphisms atoms?
So the endomorphisms, the elements of the BOA, they have to act on the module, and then you have for these operators you want to impose the same relations as for the BOA, roughly. As for Lie algebra, for example. Okay. So So this is the orbifold construction, and yeah, one problem is to understand the structure of this orbifold. And the first theorem which can help you to do that is a result from 2019 from Sven Möller and me, and this gives you the dimension of the V1 subspace. So it is very simple. We have a number 24 here, and then you have some divisors of the order. Then you have some rational numbers, and then you have something which is easy to calculate. Okay, and then you have some rest term, R3, and yeah, you can describe this rest term explicitly. What is important is that it is bounded below by 0. Okay, so this is a formula for the dimension of the V1 subspace, and yeah, there are some sufficient conditions which ensure when this here is 0, and this here, since this takes place in the original vertex algebra, this is easy to calculate. Okay, so and yeah, one question is how do you prove this? Where does this come from? This is actually the subject of the workshop, it's number theory and physics. So this is a condition which comes from the Eisenstein series. Okay, and this 24 here is essentially the 24 which you know from E2. Okay, so how does it work? So VG is a vertex operator algebra with n squared modules. So you can put the characters of all these modules into a vector valued character, and you pair it with a vector valued Eisenstein series. So the character is a vector valued modular form for the Y representation of a certain discriminant form. Then you take the Eisenstein series for the dual Y representation of weight 2. You multiply these two, then you get a modular form for SL2Z of weight 2. And then by the residue theorem, you know that the constant coefficient has to vanish. This is exactly this equation.
I guess here it's not obvious where modularity comes from when you're presented it.
Yeah, yeah, Schu's theorem tells you that's where the modularity of the characters come from. Okay, so the proof is and Eisenstein series weight 2. Okay, that's the idea. So the good thing is, yeah, that this number here is bounded below by 0. And there's one funny observation. Yeah, for certain orders, it can never be 0. And this is a consequence of the Y bound. So if the order is a prime, that gamma 0 E has positive genus, then the rest term is bounded below. Now you can guess what it is. 24. And this is a consequence of the linear bound on the coefficient of the cusp form. Not, yeah, I think you don't get it with other bounds.
Which weight do you need? Which weight do you need the minimum bound?
Weight 2.
Well, but then it's either 2.
Okay. Yeah, but it's okay.
But never mind.
Yeah. Okay, so yeah, we need it for weight 2 because the character here has weight 0 and the Eisenstein series also has weight 2. Okay, so this is one, funny remark. So now we want to define generalized dipoles, and the idea comes from here. So whenever you have an upper bound for something, you should look at the bound. Usually something interesting happens there. And this is what we will do. So we okay, so now we say that D is called our morphism is called a generalized dipole. Okay, so now we want two conditions. So first we want this here to be maximal. That means the dimension of the dimension of RG is 0. Okay, so this is one thing, and then the other thing is there's one other condition, namely that so we know this is a Lie algebra, and it has a cut-and subalgebra, and we want the dimension of this cut-and subalgebra as small as possible. So we want that the rank of this Lie algebra is minimal, and that means you can show that it's bounded below by the rank of the fixed point Lie algebra, and we want this to be equal. So this is the definition of a generalized dipole.
So I'm confused. If RG is bigger, then the dimension gets larger. So why is number one maximum? Just making mistakes.
Yeah, maximal in the sense, so the dimension cannot be bigger than this. So that's what I mean. By maximal, I mean it is exactly this number here. Okay, so these are the two conditions, and first of all, you might say it's a bit,
So what's the difference between dimension and rank?
the rank of a Lie algebra.
The rank of Lie algebra. Okay, fine,
Okay, so this is Lie algebra, and I mean the dimension of the cut-down. Okay, so this is our definition, and you might say, okay, that's a bit, so for lattice it was maybe simpler, but what is the relation to the dipoles that we know from lattices? I want to give an example. When you take a dipole in the Leech lattice, so some element in the ambient space of the Leech lattice, so you take some dipole in the Leech lattice, then this vector space here sits naturally in the vertex operator algebra of the Leech lattice. And
Nils, there's a comment online. Brandon is saying maybe there's a sign mistake on the R of G, suggesting that it should be minus R of G. Brandon, you can you can unmute and say what you mean.
I just meant that there was a question about why you say maximal instead of minimal, and I think that question is resolved if the R of G comes with a minus sign.
Um, yeah, okay. Let me see. Yes, sure, sorry.
Now it makes sense.
Thank you.
Now it's good.
Yeah, I'm sorry.
Yes, sorry to derail.
Okay, yeah, thank you for the comment. Okay, okay, yeah, so, and by the way, this is the right formula. Okay, so, yeah, okay, so, yeah, let's look at an example. So when we take a dipole of the Leech lattice, then we can associate in a natural way an automorphism of the corresponding BOA to it. So this vector space sits naturally in the BOA of the Leech lattice. So take the element, we take the exponential of this element and the zero mode, so I won't explain the notation here. So you can lift this element naturally to an element in the BOA, take the zero mode. This is an automorphism of the Leech lattice VOA, and this is actually a generalized dipole. Okay, so yeah, so in this sense, yeah, things fit together very nicely. Now, yeah, now that we have defined dipoles for VOAs, yeah, we want to see whether we have similar results as for lattices. Yeah, and the yeah.
So if it's not holomorphic, you cannot do this, or
I have, yeah, so our definition assumes holomorphic and central charge 24.
okay.
We thought about replacing central charge 24 by other central charges, but it seems that you do not get so nice expressions anymore. So central 24 seems to be very special.
Are there examples of generalized dipoles in for this case that are not dipoles?
Yes, and this will be the main point. So they are exact. So from this here, you get 23 dipoles, and the corresponding orbifolds. These are just the vertex operator algebras of the Niemeier lattices, but there are actually 50 more dipoles, and they give you all the other VOAs. So this is the main point, actually. Okay, so yeah, so what is the analog of Borcherds theorem? So this is something here later. And this goes as follows. So we have a map from the basic classes of the holes and the for the Leech lattice VOA, and we have to assume that V1 is the V1 subspace non-zero. Okay, and on the other hand, we have the holomorphic VOAs of central charge 24 with non-trivial V1 space. Okay, so we have these two so here I mean the isomorphism classes. Okay, so we have a map from here to here, and this map is just taking the orbital. Okay. So this is the analog of Borcherds theorem. So when we look at the dipoles which have non-trivial fixed point space, and then the conjugacy classes are in one-to-one correspondence with the holomorphic BOAs with non-trivial V1 space. So this here is
Do we mean V sub 1 there on the right hand side or just V overflow?
sorry.
In your map, G
Yes.
goes to where?
Yeah, the holomorphic BOAs with non-trivial V1 subspace.
Yeah, but further down there, right on the map, G goes to
Yeah, to the
V lambda.
V lambda. Oh, that's
Yeah.
a lambda. So
Yeah.
So,
So we take an orbifold of the Leech lattice.
yeah,
BOA.
so no, it's fine. Yeah.
Okay, so this is the analog of Borcherds theorem for lattices, or for Niemeier lattices. And yeah, what is the idea of the proof here? The consequence of cuts is very strange formula. So I want to say two things. So this is an abstract correspondence that does not use any classification results on both sides. Okay, that's important. And what is this formula here? This gives you so when you have a simple Lie algebra and a finite order automorphism, this formula gives you information on the dimension of the eigenspaces. That's what this formula does. And when you use it in a clever way in some average version, then you can prove that this map here is a projection. Okay, so we have we have the analog of Borcherds theorem. That means we can classify the right-hand side by classifying the left-hand side. And this can actually be done similarly to the case of lattices. So it's a bit more difficult. The classification of the dipoles in the Leech lattice is a special case of the classification of the dipoles, which we have here. And it amounts to classifying certain point configurations in the Leech lattice. But the good news is it can be done. And before I state the result, I want to associate a whole diagram to these automorphisms. And this is what I want to explain first, and then I state the classification result for these dipoles. Okay.
There are finally many of these projects.
Sorry?
There are finally many inequitable dipoles.
Yes. There are exactly 70 of them. Yeah. Let me see. The central charge. That's good. Okay, so suppose we have a dipole. Okay, then I want to associate two pieces of data to this dipole. So first of all, we have canonical projection to the orthogonal group of the Leech lattice. So that means we can associate to this element an automorphism of the Leech lattice. And this automorphism then has a characteristic polynomial, which is described by the so-called cycle shape of this element. And we denote the cycle shape by G, the phi of G. So phi of G is the cycle shape of the projection of G. If you don't know the cycle shape, then just take the characteristic polynomial. It contains the same information. And then we need some other piece of data, namely, we want to have a diagram. So how do we do that? We have lambda V1. So this is actually a Cartan subalgebra of E lambda of V. This is Cartan subalgebra. And it acts on the first twisted module with weights pi of G, let's call them pi of G. Okay, and to this finite set of weights, you can associate, that's a non-trivial statement, you can associate a Duncan diagram. And we call this maybe phi of G. And then we have the pair of these two things. This is the generalized, that's the generalized whole diagram. B. For example, when you do this, if G comes from a dipole, then this automorphism here is the identity, or maybe this is the dipole corresponding to some Niemeier lattice n. So as we know that there's a correspondence between the dipoles in the Leech lattice and the Niemeier lattices. So we take a hole corresponding to some of these lattices n. Then so this is just 1 to the 24. That means this element here is the identity. And then we take the organization of the Duncan diagram of this lattice. Okay, so, and if you use others, then you get different Duncan diagrams. What is very surprising here, you find only 11 different characteristic polynomials. Now, there could be many more, but you can only find 11 of them. Okay, and now we have this. And I can write the final theorem maybe here on the left-hand side. This is something we proved last year. So after, it's actually something we proved after the last conference. So this is, so this is a new result. So I said, maybe we can, last time I said, maybe we can use this to classify VOAs. or maybe we can classify these conjugacy classes, and this can actually be done. So you have to study point configurations in the ambient space of the Leech lattice very carefully, and then you find the following result. There are exactly 70 conjugation classes of generalized always in the homomorphism of lattice with Okay, so this is what you can show. And now, when you have this, then you get the analog of Niemeyer's theorem. So, what is missing here? First, why did I introduce the Hook diagram? The class dipole is uniquely determined by its whole diagram. Yeah, that means by a cycle shape and by a Duncan diagram. Yes, please.
Is there any restrictions on the kinds of cycle shapes that?
Yes, there are only 11 of them, and that's a bit of a surprise. Also I know one explanation for that comes from automorphic forms. So the theory of automorphic forms only allows 11 to appear. It's a bit mysterious, but not what comes out. Sven Möller and Gerald Höhn told me that they also find other cycle shapes when they classify vertex operator super algebras. Then some of the others do also appear. But yeah, I can explain using automorphic forms on orthogonal groups. This is one way to see why you get only very few of them. But maybe I can explain this after the talk. Okay, so yeah, so this is the analog of Conway, Parker, and Sloane's result, right? So we classify the dipoles, we know exactly what they are, and we associate a nice diagram to them which characterizes them. Okay, and a corollary of this result, and this will be my theorem. An application of these two theorems is, of course, the classification of your A's. After isomorphism, there are exactly 70 holomorphic UAs of central charge 24. Non-theoretically one. Okay, so we cannot say our methods don't give any information if this here vanishes. you just have, we need this space here, the Lie algebra here, to control everything. If it disappears, our methods do not give information. So, okay. And when we have such a VOA, it is uniquely, so for lattices, the root system determined everything. Here, the Lie algebra structure of V1 determines everything. Okay, so in this way, we can prove this classification theorem here, which is the analog, or almost the analog of Niemeyer's theorem. What is missing is the uniqueness of the Moonshine module. So if you allow 0 here, we expect that there's only 1, but we don't have a proof of this at the moment. What I should also add is, so the first proof of this theorem is roughly 2 years old, and it's just a combination of many, many different papers. And then there are 2 approaches to proving this result. So there's one by Sloane and Möller, who use short automorphism. So they also can prove this in a kind of unified way. And then there's also a very nice paper by Gerald Höhn from 2017, where he proves this result up to certain conjectures. Okay, so there are essentially now several proofs of this. What I like about this proof here, it's very similar to the lattice case, or similar to the lattice case and very uniform. And it uses the geometry of the Leech lattice heavily. So that's why I like this proof here.
And it's yours. It's your
Yeah, it's not mine. So it's certainly without Sven Möller, this would not exist. But yeah, so so this is essentially what I wanted to say in exactly 1 hour. So thank you very much.
Thanks a lot. Any questions?
Yes.
So you mentioned getting finiteness results for these even positive unimodular lattices. There's an automorphic proof of that.
Yes.
So
but I cannot reproduce it. It's not easy.
okay, so there's no automorphic. You're just studying.
So you mean an automorphic proof of this here, or?
No, showing that there's 70. Like finding the number 70.
So finding the number 70s.
You mentioned 24 is an Eisenstein series. Sorry, I'm sorry. You mentioned earlier that there was a proof that was not one of the 3 you wrote down.
Yes. So if you want to prove that there are 24 Niemeier lattices, then there are at least 5 proofs. So I wrote down 3 of them, and then there's another one using the Siegel mass formula, and then there's even another one which uses the classification of certain automorphic representations of O24. And so for VOAs, we have what do we have essentially? So we have we do not have a proof which is similar to the O24 proof, because there's the bridge to number theory for VOAs is not clear enough at the moment. I think that's the main reason. So for lattices, there's just much more theory available. But that's a very hard proof, at least in my opinion. I think that's true. So if we had something like this, that would be wonderful. Then maybe we can remove this condition here. So maybe the way to remove this condition here to get 71 here is actually to have more number theory entering the theory of VOAs. Maybe that's the reason. Well, that's Yeah, maybe ask me in a few years.
Next event.
Yeah, on the next event. And there's another.
Yes, I have a very similar question. I was talking about on the same line. So is there, with the lattices, there's a notion of neighboring lattices? Which
Yes.
you can use
Are there-
like the Hecke eigenforms on the O24. So is there a notion of neighboring BOAs?
Yes, I mean, yeah, so I think that the idea is two neighbors should be two orbifolds. So you should replace the neighbor theory by orbifolds. Also P neighbors are P orbifolds, that's the idea. And I hope that you can build some theory on this, but it's rather difficult. For lattices, it's easy to see that the neighborhood graph closes. Yeah, so when you take successive neighbors, then you get everything in a genus for any prime. And we have no idea why this should be true for BOAs. So then everything would be so if that would be true, then we would have the uniqueness of the moonshine module immediately. But at the moment, it's not true that you can get any holomorphic BOAs of, yeah, it's not known whether you can get any holomorphic BOA of central charge 24 by just taking one and then taking successive orbifolds. Also, yeah, if we knew something like this, that would be great. You had a question?
Well, yes, since you mentioned moonshine several times. Is there like an interpretation or these deep holes in some moonshine context? Or
yes,
how should I
there is.
think of
Also,
that?
if you can classify deep holes without this, you can throw away this condition here and still classify deep holes.
Yes.
And then you have, I don't remember the exact number, maybe 50, which give you the moonshine module. I don't know the exact number, so I would have to check it. But you can, yeah, we have the classification without this condition. But I didn't write this down because we don't have the interpretation there.
So if there are any questions on Zoom, just let me know in the chat and I will raise the volume. They seem very happy. Well then, if there are no further questions, let's thank Nils again. Well, they do say thanks for the nice talk. So there is...
Thank you.
Thank you.
It's not easy.
Yeah, so this
I mean, I've always seen this briefly.
So there's a nice interpretation. Even if you can't prove there 24, you can interpret it.
I see.
Integral structures. For instance.
So is it clear just from some, the Minkowski argument shows you that there are finitely many of these, even unimodular plus definite lattices of rank 24. Is it clear that the finiteness is like from the right hand side, the finitely many holomorphic BOAs in central charge 24?
I think. Yeah. Mhm. I don't think so. So there's, we don't have an analog of Minkowski's theorem for BOAs. And
so finiteness from the left hand side is natural state. Like it's not for
yeah, so this group is infinite here. So, and if even, I think even if you take, so it has, that's an infinite group, it has infinitely many conjugation classes, I think, and I'm not 100% sure, and I think even Yeah, when you restrict to deep holes, then yeah, then not. And maybe you can see from the left-hand side more easily that there are only finitely many. I think we have enough information on the group, on this group here to show that. I mean, I know that it is true, but I think you can. I think you can. Yeah, it's much more. I think it's more easy. Yeah, that should be possible to show that this number here, no matter whether you put in this condition or not, that this number is finite. You can use this from knowledge of this group. We do have some information on this group.
The second condition on deep holeness looked like some kind of being regular. It's some kind of.
And in what sense?
The group sense. Regular.
Yeah. Okay. Yeah. So yeah, we just found
that class like you can break up those elements in the conjugacy classes. It seems plausible.
Okay. Yeah. Okay. Yeah. We just figured out that for us it makes things nicer